702.
The Naked Scientist.
Time for us to talk science, the world of science, with Dr. Chris Smith. And we're speaking to him from, where are you this time? You in Cambridge?
Yeah, just outside Cambridge, actually. And it's not raining, although we have had some thunder, though not on the sort of scale of a Johannesburg thunderstorm. But, it's trying. We can't match you in all ways. But just been watching a really interesting story, actually. A friend of mine, James Logan, who's at the London School of Hygiene and Tropical Medicine, has teamed up with the Medical Detection Dogs group. And what they have done is to train dogs to recognise people with coronavirus infection. And the dogs are a lot better than a lateral flow test, put it that way. In fact, they're nearly as good as a PCR test. They train, big dogs like Labradors, for example, and they've been using clothing worn by people who have had a confirmed diagnosis of coronavirus infection. And the dogs are 94% sensitive at finding the people who've got the clothing on. Even if you have a little tiny piece of the sock of a person who had COVID, the dogs can find them. And the news coverage is slightly dodgy because they're saying that the dogs are smelling COVID. Now, that's not the case. What the dogs are smelling is the various volatile chemicals that come off the body of the person who is infected with coronavirus. And it is, in fact, the molecules the body makes in response to having the infection and fighting the infection that produce that unique constellation of odours that the dogs can detect. They're not actually sniffing up coronavirus particles to smell those, although they could potentially sniff up coronavirus particles. And I suppose that's one other constraint of this. Dogs can catch COVID too. Yes. So we hope that they're not being put at risk in the line of duty. But this could be a very quick and efficient way to screen queues at airports. You just wander the dog like you do a drug detection dog. You just walk the dog along the queue and it will indicate where it detects people who may potentially be right now infected with coronavirus or have had a brush with it.
Oh, my goodness. So at the airport, I think just when you see sniffer dogs, you immediately get anxious. So now
I don't know. Do you? What have you got in your luggage then, Azza? Is there something you're not telling us?
Even if you're innocent, Chris, even if you haven't done anything, just the sight of them, you start to get nervous. So now even with COVID, you think, what? Maybe? What? Oh, that little scratchy throat. Was it? Could it be? Yeah. So I think that's exciting. It's amazing.
It's good though, isn't it? Amazing how good these dogs are. Their sense of smell is, tens of to hundreds of times better than ours. And one analogy I heard was that someone said, if you could smell, because sugar doesn't have a smell, but if you could smell the smell of a teaspoonful of sugar in a cup of tea, a dog could do that teaspoonful of sugar in 2 Olympic-sized swimming pools. That's the difference in sensitivity of their sense of smell, which is how they're able to do this. They're basically picking up subtle odour cues that when your metabolism and your physiology changes because you're fighting coronavirus infection, then your metabolism shifts in such a way that you produce a tiny difference in the various molecules that just ooze out of your body in sweat and breath and so on. And the dogs can pick that up.
Astounding. Really astounding. Maybe you have a follow-up question to that, or you have your own science-related question this afternoon for the Naked Scientist. That's Dr. Chris Smith joining us now. Dennis, you've called us from Fourways. Hello.
Thank you. Yes, Doctor, I need to understand, as the universe expands, where do the galaxies get energy from to move away from each other or away from each other as opposed to what each other, simply because gravity will want the galaxies to come together and not away from each other. Thank you.
Wonderful. Thank you, Dennis.
Hi, Dennis. The answer is that when the universe was first born, and we think that happened about 13.8 billion years ago with the Big Bang, there was a point infinitesimally small but extremely energetic in space, which, the universe didn't exist. That was the birth of the universe. So it's not as though that was in space somewhere. This was everything. And it then began to inflate and blow up like a ball very, very fast. Very, very fast indeed. And it was very smooth and homogeneous. Everything was evenly spaced. But then, quite quickly, gravity takes over and pulls different entities together. So you get droplets of material which coalesce out to form galaxies and stars, separated by space. So as the universe continues to expand and cool, because if it gets bigger, it cools down because the energy is spread over a bigger area, those individual things, those entities, those galaxies are basically farther and farther apart from each other because the space between them has got bigger. Then we reach a period sort of where we are today, where you have the universe and you have galaxies distributed across space. And if we look at far away galaxies, they're going away from us, and the farther away we look, the faster they're going away from us. And this is because the universe is inflating. It's still growing, and as far as we can tell, it is growing faster with time. So the farther we go back, the smaller it was, and it's going faster at an increasing rate. So at the moment, it looks like it is expanding and expanding faster the faster it goes. So the faster it grows, the faster it goes. The distance between the galaxies is therefore getting bigger, and that's because the space separating them physically is getting bigger. Dark energy is making the universe grow, and the entities which are held locally by gravity pulling things together, they just get farther apart, not because they're moving away from each other, but because the space between them has enlarged. Now, some of them are still coming closer together. So, for instance, the Andromeda Galaxy is coming towards us, and eventually it'll get here. And our galaxy and the Andromeda Galaxy will have a bit of a brush. The Milky Way also had a collision with another galaxy a number of years back, millions of years ago, when the dinosaurs were ruling the Earth. So these things do happen. But on the grand scheme of things, the universe is getting bigger, and these galactic entities are moving apart because the space between them on cosmic scales is getting bigger.
Wow. Dennis, there you go. Thank you so much for your question. And there's some voice notes as well, so let's get to those.
Good afternoon. This is a question for the Naked Scientist. Can you please tell us how a master key works?
Oh.
Thank you very much. Bye.
Okay. How does a master key work?
Well, to understand how a key works, you have to understand how a lock works. Now, if we took a lock, the kind of thing that you just basically plug your Yale key in, and we cut it down the middle, what you would see is a whole bunch of hammers, which are sort of vertical columns of metal dropping down into the latch. And when they drop down, they lock the lock because they are basically in the way of things turning. When you thread the key in, the knobbly bits on the key, which push upwards in some places but are lower in other places, allow those hammers to rise in some areas and drop in others. And that has the effect of moving them into the right configuration so that the barrel of the lock can turn, so that they're not in the way of the barrel turning. Now, some keys and some locks are built so that you can have a key which has a specific configuration capable of moving all of the hammers out of the way in the right way, regardless of what sort of lock it goes into. They're usually all one sort of generation of lock. So they will be made by a specific company, and they have a specific way or a set of configurations so that when that key is used, it will move the hammers in just the right way so the lock can rotate. And all the locks have that particular susceptibility built into them. Now, of course, that is a risk, because if you have a situation like that, then as soon as someone copies that key, they've got access to all the doors. Whereas if you divide your building up into different departments that have slightly different keys, and you only issue keys to people and they lose one of them, you only have to change one set of locks. So you keep your eye on that master key very, very carefully.
Next, we've got Mangwe calling from Centurion. Hi, Mangwe.
Hi, Zania. Quick question. I just want to know, there's a hypothesis or theory that maybe a parallel universe.
Oh, wow. Yes, an alternative universe with the same person, but just living a different set of outcomes.
Some people are advocates of there being parallel universes. Some say there are universes hovering just a few millimeters in front of your face, but the dimension they exist in is a different one to the dimensions we exist in, and therefore we're unaware of their presence. The difference is that all the theories that predict these things, they're just that, they're theories, and there's no evidence to suggest that these parallel universes do exist yet. But we think that if they do exist, then the one thing that will transmit between them is gravity. And therefore, if there were gravitational waves in one of these universes, they ought to be able to propagate into this universe, and we would feel that effect. And so scientists are actually designing experiments that would enable them to detect that. There is a project called LISA, which is a huge interferometry array spanning massive swathes of space, which is being built up in space. And this will use laser beams, which are bounced between spacecraft in different axes. And when gravitational waves come through, it compresses the space between those space probes and it therefore changes the course that the light is following, and in that way you get a timing aberration and you can detect that some gravitational waves went through. Now that would be very useful for probing our own universe, but also potentially we could see if there's evidence of strange and mysterious gravitational waves emanating from other universes which are bobbing around as well. We just don't know. I mean, these are just one of the things in theoretical physics that could exist. One person said to me once that you could think of it as like we had a big bang that spawned our universe. Well, perhaps the big bang is a white hole, and a white hole is the backside of a black hole in another universe. So you basically take loads of stuff from one universe, crunch it down, and eject it through the white hole of your black hole, which becomes a new universe with a different set of rules, potentially. We don't know that the rules of physics that we're following in our universe apply in other universes. There may be different universes. They may have totally different rules of physics. We just don't know. And you're always very cautious because, as one theoretical cosmologist said to me recently, you know, it's a very powerful thing, this. You can prove that naught equals 1 with maths and physics. You can prove it on paper, but testing it and showing it's for real, that's a very different matter. So theories are one thing, reality is another. So theories are something we come up with on paper. We then design experiments to test whether they might be true and if those predictions exist or not. And no one's seen evidence for parallel universes yet, but watch this space, in inverted commas.
So having said that, Chris, which then is your favourite of the disciplines?
Well, actually, when I was at school, I learned it and did okay in it, but I didn't really like physics because it was loads of maths and I didn't appreciate the importance of it. I just thought it was a whole bunch of formulae and you learned the right formula and learned when to apply it, and then you got an answer and you probably had to draw a graph or something boring like that. And then as I've grown older and learned it properly, and I had to write a couple of books, including our Chris Packett Fireworks book, which was basically explaining physics to young people, I suddenly understood it properly myself and then thought, oh my goodness, how important is this? Why did no one explain this to me when I was at school like this? Because now I get it. And you suddenly realise that everything that happens around you is physics. It explains everything, the way things move, the way things behave, everything. So I'd say for pure elegance, physics, because it explains things and gets them right. It's like it's the scientific equivalent of accountancy. When you see all the columns line up and all the numbers are right, then you get this big rush of satisfaction. That definitely works. For fun and understanding our own existence, biology definitely, because it never ceases to amaze me what animals and the world and the planet does.
Wow. Next, let's go to Ntabiseng, calling from Soweto. Ntabiseng?
Hi, how are you?
Good, how are you?
Good. I would like to ask as to what causes a bad dream or a nightmare, or a dream at all. Yeah.
Or no dream at all.
No, or a dream.
Oh, okay, regular dream. Okay. What causes a dream or even a nightmare?
Well, we think dreaming is incredibly important because we all do it, and we also see that animals all do it too. And for something to be that strongly conserved by evolution argues that dreaming and the period of sleep when dreaming happens, called REM sleep, REM, rapid eye movement sleep, there must be something physiologically and neurologically incredibly important about this activity. When we go to sleep, we don't just go unconscious. Our brain goes through cycles of periods of very, very slow, low activity, interspersed with periods of frantic activity that border on almost wakefulness. And as you go through the night, those periods of frantic, frenetic, high-level brain activity increase in length and duration. And so when you wake up in the morning, the reason you often remember having been dreaming is because dreaming happens during those periods of REM sleep. And the most detailed, colourful, exciting dreams tend to happen when you are closest to waking, because they're closest to the morning when you're having the longest phases of REM sleep, and you're more likely, therefore, to wake up and more likely to remember them. But we don't really understand why we dream. We understand the mechanics neurologically of what turns on REM sleep and why it probably happens in terms of what the nerve cells are doing. But we have no idea why it's so fundamentally important. We have no idea why we dream what we dream. It's probably just disparate brain activity from disparate parts of the brain which dissociate themselves when we go to sleep. Because when we're awake, the brain is divided up into different areas that do different jobs. So you have a feeling part, a seeing part, a moving part, a thinking and planning part. Those areas are all coordinated in their activity and talking to each other. But when you go to sleep, they dissociate themselves apart from each other. And although there is a common language of brainwaves which runs across the brain continuously when we're asleep, the same coordinated I do this, so you do this, handing on the messages type thinking disappears. And so therefore you probably uncouple your brain from the normal constraints of sort of social controls and rational thought and so on, and you experience these really bizarre things. It's hard to argue, though, that they're not going to be informed by your day-to-day experiences, because otherwise we wouldn't dream about the experiences we're having anyway. So it must be that you delve into your memory banks of all of your colour memories, sound memories, emotional memories, things that you've been planning and thinking about, things that have happened to you, and all of those memories can be re-executed and played and then presented to your subconscious. And you experience them, and because you don't know you're asleep, you don't realise that they're a dream until you wake up and think, oh, thank goodness that was just a dream, which is why they're so real to us, because we just don't realise we're asleep at the time. But why we do it, we don't know. But what we do know is if you don't do it, then you're much less well psychologically, much more prone to other problems in your health. And if you don't sleep at all, you go mad. So sleep, very, very important, but it's very much a black box that we don't understand.
Excellent. Let's squeeze in this voice note because we have a very few minutes remaining and see how much we can get
Hi,
through.
Dr. Chris. I just want to find out what is it that makes women to go early labor?
Oh,
You know, the other ones who give birth at 6 months, some 7 months. So I just want to know what is it that is triggering that? Thank you.
We don't
there's
know.
biology there.
There's a range of reasons why people have preterm labour. Some people, it runs in families, and therefore one anticipates there must be some kind of genetic impact on it. Sometimes infection can cause this. If you catch certain infections during pregnancy, they can cause irritation to the membranes around the developing baby and therefore irritation to the uterus. And inflammation is one of the signals that the uterus is triggered by. Also, if you have multiple pregnancies, so you have a very distended uterus, the stretch in the uterus is also a stimulus to give birth, because that's part of the way in which the uterus works out how big it is and therefore how near term you must be. So the answer is there's no one single factor, but some good news is that scientists recently did a study where they have found a number of chemicals in the bloodstream. They actually used a machine learning system like artificial intelligence to track the levels of these different chemicals in the bloodstream and then compare them with when a woman gave birth. And they were able to narrow the window of predicted birth time from a normal prediction window of 5 weeks. Your baby's going to turn up sometime between this time and 5 weeks later, down to just 2 weeks, which that's quite a big improvement. It's not quite this day, but it's quite a big improvement. And what that does mean is you would make more accurate predictions about people who might be at risk of preterm labour. And if you know that's going to happen, you can do things before the labour initiates to stop the labour initiating, because you don't want babies coming out too early, because they do need to cook for longer, because they get various benefits in terms of their growth, lung maturation, and other things such as the movement from the mum's bloodstream into the baby's bloodstream of important antibodies which are critical for immunity.
Okay, I'm going to be a little naughty and squeeze Arthur's question. Arthur, please make it brief.
Okay, thank you. I just want to ask a question.
Yes.
I had COVID this month, and on 10th of this month I tested negative. But I had no symptom at all, absolutely nothing. I want to know how long do I have to wait for me to get the vaccine?
All right. Chris, how long does he have to wait?
The answer is, Arthur, that if you've recovered from COVID, you do have antibody and an immune response already, because that's how you recovered, assuming that it wasn't a false positive on the test, and that's not a certainty. But once you're better and feeling fine in yourself, or if you had no symptoms whatsoever, there is no impediment to going and having the vaccine. If you do have the vaccine off the back of a recent history of coronavirus, what it will do is stimulate the immune memory you have already made and reinforce it. If, on the other hand, it was a false positive test result and you don't have any immune memory, then you will make one. And either way, you're a winner.
Fantastic. Arthur, there you go. Chris, thank you very much.
Pleasure.
Until next week.
All right, I'm looking forward to it already.
Yes, me too, Dr. Chris Smith.